Hello, and welcome to Empowered Learning. This video is about the fundamental theorem of calculus, the net change theorem, the average value theorem, and seeing how we can actually use the fundamental theorem of calculus to be able to evaluate definite intervals. So first, let's get started with the two parts of the fundamental theorem of calculus. The fundamental theorem of calculus, its purpose is to bridge what's called the differential part of calculus and the integral part of calculus. And so if you've been studying this subject and you're looking at this video now, then you've probably studied antiderivatives before. And so what the fundamental theorem of calculus does, it connects what the meaning of taking an antiderivative is, and it says that, hey, when we take that antiderivative, it is essentially giving us a mechanical way to figure out the area under the curve of a particular function in between some x value a and another x value b. And so the fundamental theorem of calculus is broken up into two parts to first address the, the inverse nature of an antiderivative and a derivative. And then the second part to address how do we actually mechanically evaluate what the area under a curve of some function will be in between two x values. So the fundamental theorem of calculus part 1 says if f is continuous on some closed x value interval from a to b, then we can find the antiderivative of that little function f by taking the integral of the little function f with respect to t, evaluated from x equals a to some other value of x. We can do all that. We're saying that the antiderivative is also continuous from x equals a to x equals b, and it's also differentiable on the open interval from x equals a to x equals b. So basically what that first part is saying is that, hey, if my little function f is continuous on a to b, then the antiderivative is also continuous and is differentiable. And how it is differentiable is unique in that when we take the derivative of the antiderivative, we indeed just get the original function f back again. And so that is why you see where it says, and its derivative is f of x, meaning that the antiderivative, if we take the first derivative of that, we see that by doing this, we end up getting the function f of x back again. Now, of course, here, this x equals a, that's just a constant. So you're going to see when we talk about the second part of this theorem why they don't mention anything about the a that's in here, okay? But again, this theorem is basically saying, hey, if we have some function that we want to take the antiderivative of over some closed interval of x values, then its antiderivative is also going to be continuous and is going to be differentiable, meaning that we can take the derivative anywhere in between x equals a and x equals b, and we specifically define the derivative of the antiderivative of little f as just being the inverse function of, or the inverse operation of taking the integral of little f of t. And so essentially what is happening here, without trying to do too much, now erase this, is we see that the Leibniz form of a derivative and the infinite sum, they are essentially undoing each other. And because we're considering this evaluated over x here, this just ends up being like that. And so we'll see in the next part of this why it actually ends up being that way. And so the second part of the fundamental theorem of calculus it's basically telling us how we can mechanically find the area under the curve of little f of x from x equals a to x equals b. And it says that if f is continuous at every point in the closed interval from x equals a and x equals b, and we know that f is bigger F is the antiderivative of little f on this same closed interval, then what we can do is take the antiderivative and evaluate it at b minus evaluate the antiderivative at a, which is our limits of integration here, and that will give us a precise measure of the area under the curve of the function little f of x from x equals a to x equals b. So this is sort of the mechanical way of figuring that out. And so that is what fundamental theorem of calculus allows us to do. In practical use, we're going to use more so this part of the fundamental theorem of calculus, but this part here, part one, has to be said first because we have to make sure that we know that the antiderivative and a derivative are both continuous over the same closed interval of x values, and we have to make sure that the antiderivative is differentiable so that we can get little f of x back again if needed. Okay, and so thus what we've done is we've connected an antiderivative with the derivative and showed that relationship, as well as shown that the area under a curve of a function is related to taking the antiderivative of a function and evaluating it over the difference of its limits of integration. Okay. So moving on to here, because of the second part of the fundamental theorem of calculus, we now can state what's called the net change theorem. And of course, we know from the fundamental theorem of calculus here, little f of x here is essentially what big f of x and take the derivative of that would be. So the net change theorem, the only thing that changes now is that we can replace little f of x with the antiderivative of f and then take the derivative of it and replace it by being that. Okay, so not much new here. The mean value theorem for definite integrals says that if f is continuous on this closed interval, then at some point we know that there is some value f of c that is going to be equal to taking the area under the curve of this function evaluated from a to b, and we're going to multiply that by 1 over b minus a. Okay, so in essence, what we're trying to say here is that if we were trying to get an average of what the area under the curve would be, of course, the b minus a would be the width of that particular rectangle that would be formed, and f of c would be the corresponding height of the rectangle that's formed to come up with that average. Okay? So moving on to the next page here, we see some graphical depiction of this. So f of c, again, here is the average height of this rectangle that you see here in pink. And of course, we have some overage that's over here in pink, but we also see that the rectangular area does not get this part. So in general, what we're saying is that these two things are approximately equal. Not exactly equal, but approximately. So the value of f of c in the mean value theorem is, in a sense, the average or mean height of the function little f of x on this closed interval. And we also assume that if the function little f is above or on the x-axis, then the area of the rectangle is an area under the graph of f of x from x equals a to x equals b. And so here, what we're trying to illuminate in this case is that in the cases where we have a function little f of x that is not continuous from x equals a to x equals b, then we don't consider having average values for that particular function. Okay? So hence, if we come back here, that's why it says if f is continuous on x equals a to x equals b. If we don't have that set up, we don't consider, or it doesn't make any sense for us to talk about the average value of the function. Okay, so moving on. So now we're going to look at the net change theorem and use the net change theorem to be able to evaluate these definite intervals. So for this one, if we wanted to evaluate this, first thing that we notice is that we have a constant, so we can pull that out, and then we just have e to the x dx left. Now, we all know that this is supposed to be little f of x, and if we take the antiderivative of e to the x, we all know that that is just e to the x, because e to the x is the derivative of itself. And we are going to evaluate that from -1 to 2. And so here what that means, in this case, according to the net change theorem, remember this is your b, and this should be a -1 here. That is your a, so we're doing f of b first, which means e of 2 minus, and then here we do e of -1. And of course, from here, just is a matter of how you want to, try to simplify this. I'll just say e squared over 1 over e. And then from this point, we can just say 2 times e cubed minus 1 over e. And we can just leave it like that. So this value here is the exact value of the area under the curve of the function 2e to the x from -1 to 2. And so if we were to draw that, of course, e to the x kind of looks like this. -1 is here, 2 is there, and we're looking at all this area that is here. And so of course you could go into your calculator and type that in and figure out what that exact value is. Okay. All right, for our next example, you see that we're just looking at the area under the curve of this parabola, which is -3x squared from x equals 0 to x equals 1. And of course, for here, we just pull out the constant, and then after that, we just take the antiderivative of x squared according to what the net change theorem in the second part of fundamental theorem of calculus tells us. And so we use those antiderivative power rules to basically get x cubed divided by 3. And we're going to evaluate that from x equals 0 to x equals 1. And of course, came here and just factored out the 1/3 so that I know that that's -1. And I plug in 1 for x here, minus, and then plug in 0. And we see that we finally end up with the answer of -1. So the net area under the curve of -3x squared from 0 to 1 is just 1 square unit. Okay? And so now, in this next example, we're asked to find the area under the curve for the function f of x is equal to 1 over x. And we're asked to do that from x equals 4 to x equals 7. So this area will just be 4 to 7, 1 over x dx. And so if you remember, we know that the derivative of natural log of an absolute value of x is just 1 over x. And since the limits of integration that we're considering here are all non-negative numbers, or really they're all positive numbers, then we don't have to worry about the absolute value of x part. So here what we can say is that the antiderivative of 1 over x in this situation is actually just natural log of x and we can evaluate that from 4 to 7, which means we have natural log of 7 minus natural log of 4. And of course, if we wanted to use our logarithm rules, we could just write it this way. And of course, whatever that number is would be what the exact area under the curve of that function would be. Okay? For example D, first thing that we would want to do here is rewrite this as x raised to the negative 2 dx, because now we know how to take the antiderivative of this by just using our power rules. So here this would be x raised to the negative 2 plus 1 over negative 2 plus 1, and all that is evaluated from negative 1 to 4. And so if we're cleaning this up here, we know that this is essentially going to be negative 2 plus 1 is going to be a negative 1. And so 1 divided by a negative 1. So I'll put it like this. 1 divided by a negative 1. Factor that out. And this here would just be x raised to the negative 1, which we know is just another way of saying 1 over x. And we will evaluate that from negative 1 to 4. Okay? And so now to finish this up, we know that 1 over negative 1 is just a negative 1 times, and now we have 1 divided by 4 minus 1 divided by a negative 1, which gives us negative 1/4 plus 1, and this would essentially give us negative, and 1 could be the same as 4 over 4. So I'll go ahead and erase that and put that in. And so now we have 5/4. So our answer here is negative 5/4. And so what this is telling us is that the area under the curve for this particular function somehow, some way, ends up being below the x-axis instead of above the x-axis. So if we think about this for a second, we find this to be a strange answer. And here's the reason I say that. If we look at what 1 over x squared looks like, and I'm going to bring up another screen here so that we can talk about that for a second. So let's talk about this. 1 over x squared is the square reciprocal function. And so that function looks like this, where you have a vertical asymptote at x equals 0. And what we're asked is to find the area under the curve from basically negative 1 to 4, which is all this. If you're thinking about what I'm thinking, then you'll realize that when we ask this question here of basically what is the area under the curve of this function from negative 1 to 4, if you realize what the graph looks like, we know that there's no answer for that. And the reason that there is no answer for that is because our function, which is 1 over x squared, is a function that is not continuous from negative 1 to 4. Okay? So since the function is not continuous from negative 1 to 4, there's no way that we can really compute what the area of this function is from that. So we've basically violated the fundamental theorem of calculus. And so I did all this just to show you that if we just sort of blindly follow what's going on, we'll look at this answer here and think that it makes sense, but really it doesn't. And so we have to know before we start actually doing integration to our functions, if the function is going to be continuous for every value on and in between its limits of integration. Okay? So for here, we've done all of this for nothing. And so what I'm going to do now is erase all of this and just say that, hey, you know what? This answer cannot be, well, this particular integral can't be evaluated because our function here is not continuous. Okay? So all this stuff that we've done has been for nothing. But this is a good lesson to let you know that, hey, we just can't blindly go and start calculating definite integrals without first considering what function it is that we're dealing with and its domain. And thus, if we think about its domain, we're also thinking about continuity of the function. All right, so now that we've done that, we know that we just have no solution to that. All right, so let's look back now and do some more definite integrals. So when we look at this particular function, x minus 1 over square root of x, the first thing that we want to make sure of, and lead to that other problem that we talked about, where we did all that work and we found out that we really shouldn't have taken the integral in the first place. We need to make sure that 1 and 9 are going to be values that are in the domain of our function here, as well as any other values that are in between. Now, the domain of the function x minus 1 divided by square root of x is just all values of x that are greater than 0. And of course, 1 through 9 satisfies that, so we don't have any issues there. So we can indeed take the definite integral of this. So to start off, one of the things that we want to do is rewrite x minus 1 divided by square root of x. And of course, we know that square root of x is just x raised to the 1/2. And if we split this up into two separate fractions, it will look like this. So now we can consider this as being x raised to the 2 over 2. So that would just be x to the 1/2 minus x to the negative 1/2 per our exponential rules. So what all this means now is that when we come here and rewrite this integral, then this will be from 1 to 9 of x raised to the 1/2 minus x raised to the negative 1/2 dx. And of course, at this point, we can just use our power rules to evaluate this. So here we have x raised to the 1/2 plus 1 over 1/2 plus 1 minus x raised to the negative 1/2 plus 1 over negative 1/2 plus 1. And all that will be evaluated from 1 to 9. So from that point, we'll just clean this up and then evaluate. So I'll come over here. So now we know that 1/2 plus 1 is like 3 over 2. And so we have the same thing in denominator, 3 over 2, but the reciprocal of 3 over 2 is 2 over 3. So that would be 2 over 3 times x raised to the 3 over 2. And again, I'm doing that because this portion here ends up being 3 over 2. So if I have something divided by 3 over 2, the reciprocal of that is just 2 over 3. So that's why I have that there. And of course, the x raised to the 1/2 plus 1 is just x raised to the 3/2. Okay? So I want to make sure I was clear on that just in case you got lost in those steps. All right, so now for the second term, we have same kind of thing here, but now we have negative 1/2 plus 1, which gives us a positive 1/2 in the denominator, but 1 over a positive 1/2 ends up actually just being 2, because that's the reciprocal. And then we'll just say here times x raised to the 1/2. And of course, all of that will be evaluated from 1 to 9 again. And so now from this point, this looks a little bit more clean, so we can go ahead and finish up. So only other thing I would want to do here is just say this is 2/3 times, and now say square root of x cubed minus 2 times square root of x. So that way we can deal with it in a form that we're a little bit more familiar with. So now at this point, we'll just come and evaluate. So for the antiderivative evaluated at b, we'll have 2/3 times 9 cubed, and here we'll also have 2 times square root of 9. So that will be the first term. And then we'll say minus, and then say 2/3 square root of 1 cubed minus 2 times square root of 1. Okay. All right, so now in evaluating this, we see that square root of 9 cubed is just like saying square root of 9 times square root of 9 times square root of 9. And of course, we know that square root of 9 is just 3. So for each of these, we have 3 times 3 times 3, which is 27. So this would be 2/3 times 27 minus, of course, square root of 9 is 3. So 2 times 3 is 6. So that would be first term there. And then for the second term, we know that square root of, we know that 1 cubed is 1, and square root of 1 is just 1. So we just have 2/3 here minus 2 times square root of 1, which is just 1, so that'll just be 2. So we have that. And of course, now we know that 3 goes into 27 9 times. So that will reduce to 1, that will reduce to 9. And now we have 2 times 9, which is 18. So that's 18 minus 6 for the first term. And then of course here, we know that 2 is the same thing as 6 divided by 3. So I'll go ahead and replace that. And of course, 2/3 minus 6/3 is going to give us a negative 4/3. But of course, a negative times a negative is a positive. So come here, 4/3. And of course, on this, the 18 minus 6 is just 12. So we just have 12 plus 4/3. And we know that 4/3 is like 1 and 1/3. So this will be 13 1/3. And of course, 13 and 1/3 is the same as 40 over 3. So we'll move a little bit here and make that 40 over 3 square units there. And so that would be the answer for A here. So now we're going to go ahead and move on to example B. So for our next example, we see that we're wanting to find the area under the curve of secant squared t from 0 to pi over 4. And so if you remember from your derivatives, we know that the derivative of tangent is secant squared. So for here, if we were wanting to do this, this actually turns out to be very easy because now we know that the antiderivative of this is just tangent of t, and we're going to evaluate this from 0 to pi over 4. And of course, this would be tangent of pi over 4 minus tangent of 0, radians. And so from here, if you remember, for tangent, pi over 4 is like 45 degrees, and tangent of pi over 4 is just 1. And tangent of 0 is just 0. So our answer here is just 1 square unit. All right, so for our next example, we see that now we have 4 divided by the square root of 1 minus x squared dx, and that is being evaluated from 1/2 to 1 divided by the square root of 2. Okay, and so here, if you recognize, if we pull out the 4 that's here, factor that out, and we just have this left, you'll recognize that 1 over square root of 1 minus x squared is the derivative for inverse sine, or arc sine. So once we factor out that 4, then we just realize, hey, that's nothing more than a derivative for sine inverse. So we just take the antiderivative, which is sine inverse, and evaluate that from 1/2 to 1 over square root of 2. And of course, we do f of b, big F of b, minus big F of a. And so now from here, we realize that sine inverse of 1 over square root of 2 and sine inverse of 1/2 are just angles. And over here, if you use right angle trigonometry to remember this, we'll see that for 1 over square root of 2, since we know that 1 over square root of 2, that ratio is positive, we can look at it as being in quadrant 1, and we know that 1 is here, square root of 2 is there, so that is like sine of 45 degrees, a sine of pi over 4. So hence the actual angle would be pi over 4. And same deal with sine inverse of 1/2. Since it's positive, we can look at it being in quadrant 1. So 1/2, that would be sine of, in this case, since this is a 1, square root of 3 on this side and 2, 1 corresponds to the smallest angle in a 30, 60, 90 triangle. So that would be 30 degrees or pi over 6 radians. And so keeping everything in radians, we have it written like this. And then, of course, we just combine like terms to come up with with some common denominator. Well, not combine like terms. I mean, we have to find a common denominator. And so all I did here was kind of do the quick move of multiplying that times that, that times that, and then that times that. And then afterwards, do what we can to simplify. And you see that we end up just having pi over 3 square units. All right, moving on to the next example. You see here that we want to find the definite integral, or the area under the curve, of this particular function from 0 to 1. And when we look at this, we have to remember that e is an irrational number, approximately equal to 2.71. So we're going to treat this just as if we just had an x squared here. Okay? So if we do that, then we know that when we take the antiderivative, that this is going to follow the power rule. So this will be e x raised to the e plus 1 over e plus 1 plus, and the antiderivative of e to the x is just e to the x. And we will evaluate that from 0 to 1. And so first thing we'll do is plug in 1, or evaluate this at 1, and then turn around and evaluate it at 0. So I'll come over here and do that. So we have 1 raised to the e plus 1 over e plus 1 plus e raised to the 1. That's the first term there. Minus, now we plug in 0 everywhere. So 0, e raised to the e plus 1. All that is divided by e plus 1 plus e to the 0. Okay? So 1 raised to the anything is just 1. So we just have 1 over e plus 1 plus e, and then 0 raised to the n of thing is 0. So that whole term goes to 0. And e raised to the 0 is 1. So we just have a minus 1 here. And of course, we could keep it like this, or we can make this into a common quotient. I'm not going to do it this time and just leave it like this, but whatever units that we're in, this will be square units, and thus 1 over e plus 1 plus e minus 1, whatever that number is, would be the exact area of the curve of this function from 0 to 1. All right, so now we've done some basic definite integral integration in using the net change theorem and antiderivatives to be able to figure out exact values of the area under the curve of a function from one x value to another. So now we're just going to do some simple application problems here. And we're going to start off with this one, which says that if we know that f of 1 is equal to 12, or put another way, we know that the point 1, 12 is on the graph of some function f of x. And we also know that the derivative of f of x is continuous, and we also know that the area under the curve of the derivative of the function f from 1 to 4 is 17. We want to know what f of 4 is. So what this essentially is trying to get us to do is exercise the second part of the net change theorem, which is related to the second part of the fundamental theorem of calculus. Okay. Now, if we remember here that the antiderivative of f prime of x is just f of x. And so by the second part of the fundamental theorem of calculus and the net change theorem, we could rewrite this as just f of 4 minus f of 1. And so now, in knowing that, we say 17 is equal to f of 4 minus f of 1, which is 12. And so, of course, from there, if we add 12 to both sides, we'll see here that in this case, and let me just erase that since I'm going vertical here, that f of 4 would just be 29. Okay? So moving on to our next example here. What we want to do in this case is sketch a graph of the area represented by the function g of x, and then we want to find its derivative in two different ways. We want to find the derivative first by using the first part of the fundamental theorem of calculus, and then we want to do it again by using the second fundamental theorem of calculus, in other words, the part 2 of it, and differentiating that result to get to our answer. So I'm going to move on to the next page here so I can get to a graph so that we can actually talk about drawing what the area under this curve looks like. Okay. So if we look here, we know that our basic sine function, this looks like a wave. This looks like this. And so since we have f of t, looks like derivative. So let me erase that and start over. This looks like f of t is equal to 2 plus sine t. Then that means that our sine function here is going to be vertically shifted up by 2 units. Okay. So if we go up 1, 2, we will start here. And if I go up 1 unit, it won't go any higher than this, and it won't go any lower than that. And so I'm assuming that all of these divisions here are going to be pi over 4 units here. So that means when sine is pi over 2 or 90 degrees, it's going to go up all the way to 1. And then if we skip 2 over to pi, then it should be all the way down here. And then we keep on going, another 2. Let's see, this is 0, and then pi over 2, and then, yeah, that should be pi. So put that in the wrong spot there. So 2 over pi should be here, then another 2 pi should be down here, and then another 2 pi should be here. I mean, a point should be there, and then another 2, it should be like this. And so, of course, that will just keep on going and going. So here, another 2 over, it'll be down, another 2 over, it'll be like this, another 2 over, it'll be up, another 2 over, it'll be like that, another 2 over, it'll be down. And of course, if we just draw, messed that up there. Let's try to see if we can get it going again. And so, of course, if we kept on going here, we know that the area under the curve is going to be all this stuff here. Now, of course, we would want to stop this or enclose it within some closed interval of x values to be able to get a definite area. But for right now, since we don't have that, now the most that we can do is what I've done here. Okay? So going back to our example now, we see that now what we need to do is figure out what the derivative of g of x is going to be in 2 ways. All right, so the first way is following the fundamental theorem of calculus. And so the fundamental theorem of calculus says that, well, for part 1, says that we know that whatever this is going to be the is going to be the derivative of the antiderivative here, but it has to be with respect to this variable here, which is x. So using that, this is pretty simple. We can just say g of x is equal to 2 plus sine x, and we're done. Using it the other way, we can actually take the integral of this, or take the antiderivative and evaluate it over the limits of integration, and then undo it by taking the derivative, and we'll see that we end up getting the same thing. So if we do that, then of course, looking at this from 0 to x of 2 plus sine of t dt, this is the same as saying the antiderivative of any constant is just that constant times x, well, in this case times t, since my variable here is with respect to t, so I need to make sure I put that there. And this is plus the antiderivative of sine is a negative cosine. So I'll come here and change that plus to a minus and do minus cosine of t. And we will be evaluating that from 0 to x. And so, of course, evaluating at x, I'll just get this. And evaluating it at 0, I'll get 2 times 0. That didn't turn out so good. So we got 2 times 0, which is just 0, minus cosine of 0. And we know that cosine of 0 is just 1. So once we're done here, we see that we have 2x minus cosine x, and of course a negative times a negative is a positive. And so what you actually see here is the specific case of the most general antiderivative. when we know that x is equal to 0. So now, here we know that this is what g of x is going to be. So now when we take the derivative of g of x, we know that the derivative of 2x is just 2, and the derivative of what is the cosine here is going to be minus sine, and so a negative times a negative is going to give us a positive. And of course, the derivative of any constant is 0. And so you can either write plus 0, it doesn't matter. But at the end of the day, you see that we get the same thing. So this concludes the video of talking about the fundamental theorem of calculus, the net change theorem, and the average value theorem for definite integrals. The next video that I'll do will talk about another application of definite integral integration, which is finding out displacement versus distance if we're given a velocity function.